So welcome everyone. How many new faces do we have? Oh, wow, good. They keep coming. Keep coming. Good. My name is Tom Stabline, and Dana and I host this meetup. I'm a faculty member at USF. I also have a startup focused on Gen AI, and anybody wants to talk about that stuff after, happy to do that. The program that I'm the director of at USF, in addition to being faculty, I'm the director of a master's in artificial intelligence and business analytics. So that's what the brochures are around here, and that's what pays for this food. So you have to listen to me for a couple minutes. If anyone's interested in getting an advanced STEM degree, it's for working professionals on the weekends. Penelope, Rachel, and we have a few students who are in the program now here, so you can speak to them or me after. Happy to help you learn more about the program. I won't take any more of Alex's time. We're lucky to have one of our most valued members speak, and that's what we do at these meetings. It's membership driven. So if you want to speak at some point, or you have a topic you think you'd like to lay out there and have folks comment on and engage in discussion with, then please just speak to me or Dana, and we'll get you on the docket this fall. So, and that's how this meetup works, right? We just use members to come and talk about something interesting and share some food and non-alcoholic drinks. So Alex Delgado, why don't you take over?
Thank you. Thank you. All right. So quick question to the group here. Who here has worked with relational database or data warehouse or any kind of database technology? Just raise your hands. All right. So looks like 2/3 of everyone. Excellent. So this should be applicable to most of the folks here, which is good. I'm first going to go over, definitions, differences, and then basically undermine myself and go with a different way of how we actually store the data, how that really derives the performance difference. All right, so relational databases and data warehouses. All right, so quick recap. What's a relational database? A relational database is normally a relational database is used to store structured tabular data. It allows you to run queries on it with SQL, so you can basically access your data. It's stored relationally, and a lot of it is used for transactional data processing. So quick overview of this. Some of the most popular ones are Postgres, MySQL, SQL Server, Oracle, and SQLite. All right, and data warehouses. Basically, a data warehouse is a data store that's meant for analyzing data. Instead of really doing transactional data, it's more meant for analyzing the data and trying to get insights from it, and it's very read heavy. Some more popular ones are Snowflake, Databricks, Apache Hive, Single Store, Teradata. Kind of quick overview there. So question, so what are some of the similarities between a data warehouse and a traditional relational database? Just feel free to chime in. Or SQL, that's a good one. What else?
Database.
No. Databases both have tabular data.
Structured versus unstructured.
Yep, they all can support all of that. And
so I read about like big data.
Mhm.
Things I read about it is what I think the phrase I saw was optimistic concurrency control. So I'm sort of curious about that. So at some point in the talk, not now necessarily, but that's an interesting concept.
So remind me at the end of the presentation, because once you go through the physical storage layer, that will help drive if it's possible concurrency or not.
Okay.
That's actually a good point, but you're just way ahead of me on that one.
Okay. Put it on the table.
Cool, cool. All right, so as mentioned earlier, table data, that's nothing too unexpected. They can use SQL, as mentioned earlier, that's good. And you're to join tables together. So a lot of data is relational in nature. You can join it and get additional insights, create more complex data structures from how you can join the data together. No, this is not that hard of a question. Now, this is a harder question. What is the difference between a data warehouse and a relational database? Let's go down those. So,
relational databases based on data warehouse.
Mhm.
It's like different things. I think the idea is that you're trying to select specific columns from the database, but you don't care about every single column. Whereas a relational database, it's more like you're writing and you write rows at a time. You don't write columns.
That's fantastic. You actually gave a fantastic sneak preview to the second half of the presentation. I saw another hand up here in the middle.
Well, the data warehouse is typically used for analytical type workloads, whereas relational databases are transactional.
All right, and
Yeah, well, basically, yes, I mean, how you would ingest data, how it's stored, so.
And I'm going to be a bit of a maybe potentially ruin my own presentation real quick. So when you say there's differences, one's more transactional, the other one's more analytical. Do you know what that means in terms of like the physical characteristics of the data that makes it different?
I got quite a more of a question. So I know what a mathematical function is, I know what a mathematical relation is. So
Mhm.
relational databases, the concept that one of the concepts is relation.
Mhm.
Are data warehouses also based on the mathematical relation?
Yes, they both are accessed via SQL, and they allow you to have these joins between tables to get it's basically relational algebra. So it's the exact same concept, exact same access.
Thank you.
You're talking about like how they're stored, right?
Mhm.
Aren't like most analytical workloads are stored as like columns, so like
Yep.
localities.
I mean, so thank you for that. We're getting plenty of sneak previews what's coming up. So we're here so one of the common things given twice is columns versus rows. I'm gonna go into a lot more detail on that later on, and that's a good point. So this kind of undermines my next thing where it says it's more of a difference or more guidelines. There are guidelines, it's hard to find fast definition between the two, but the use case and how it's stored tend to be strong correlations. So I asked ChatGPT after some bullying to give me a comical answer on the differences between the two. And as per ChatGPT, trying to differentiate between a database and a data warehouse is distinguish between a garden node and a mythical creature. Both involve storing data. The one is a cute decorational, the other one is stuff, legends and fantasies. Databases are color-coded, rule-abiding students of the data world, while data warehouses are the wild, unstructured rebels who care less about precious schemes. So good luck finding a clear-cut distinction between the murky swamp of data confusion. So, took some bullying to get that, but I was able to get that out of ChatGPT. So as mentioned earlier, one of the best ways to really distinguish the difference between a database and a data warehouse is how it physically stores data. As mentioned earlier, twice, row stores and column stores and how we actually store the data. So just by raise of hands, who actually knows the difference between a row store data set and a column store data set? All right, so we got a few hands over there and a few over there too. All right, that is good. For those who don't know, the answer is really, really simple. Oh, my bad. Yeah, relational databases tend to default to using row stores and data warehouses tend to default to column stores. As you get deeper into the differences between the two, you'll really see how the row store data structure helps traditional relational databases for their use case, and how for data warehouses, column stores really and maximize performance characteristics of that individual solution. All right, so jump a bit ahead. Say a row store, column store. All we're really referring to is how the data is physically stored. So in a row store, it literally stores each row sequentially on the storage medium. So you basically get row one, stores the data, row two, stores the data. Column store is the inverse. It stores the data where all the columns are sequentially in order and all the rows are segregated. So this is still very abstract. This is not that much in the weeds. And this is basically the question we're trying to answer is what is the impact or what is the difference between row store and column store physically and how that affects the performance and the solution that we're working with. So after all that precursor, now we can get to what I want to talk about. Data. I'm going to pass this around the room here. Take a look, play around with it, pass it along. So I'm going to use the data along. What happens if the data you're trying to store, trying to access is bigger than a single sector? Well, your data is more at the not made that point just yet. So if your data is a single sector, it needs to access multiple sectors to access all that data. If your data is, I'm using an example here. So if your data is laid out sequentially, it really helps with read performance. And if it's accessed all over the platter, it slows it down. What I mean by that is, for example, if your hard drive has basically a large file, let's say a gigabyte file, if all the individual sectors are sequentially right next to each other, the head doesn't need to move that much. So the platter can spin and the head can read the data right in order it's all lined up nice sequentially. Now, if your file is fragmented all over the place, your head has to go here, and then you spin the platter a bit further, and your arms to move a bit further, and it take a lot longer because you're waiting for this platter to physically spin at 72,000 RPMs, 7,200 RPMs, and the head of the arm to really come out and read the individual file. So that is a big characteristic between how data access works. Feel free to take a look at that and pass it down. So any questions on how hard drives physically store data after just on this slide right here? How you have the platter, you have individual collections of sectors, and how all the data is lined up on the hard drive. Oh, question.
If I'm understanding correctly, similar to like
Yes, like a record player. That's a fantastic example. Sequential access is basically the record player playing nice and in order. Random would be like you picking the head up and dropping it over and over at random spots because you like certain notes. We don't want to hear the whole song. That's actually a fantastic example, and I wish I thought about it earlier. So yeah, this is how hard drives are laid out. As mentioned earlier, sequential. Oh, I see a hand up.
How does this differ for solid state?
That I will go into a bit later. That's actually like you're about 4 slides ahead of me right now there. So when it comes to sequential access versus random access, as I mentioned earlier, if all the sectors are right in a row, basically the head doesn't move that far, and accessing the data sequentially is much easier. When it comes to random access, if you have to go from sectors all over the platter, jumping back and forth, and you're basically really stressing out the equipment to be able to get you all data you need. Did I see a hand up? Nope. Oh, my bad. All right, cool. Any questions on sequential versus random access? All right, I'll take that as a no then. So actually, this is kind of a blast from the past. Raise your hands. Who here has defragmented a hard drive in the past? All right, so I hope if you've ever done disk defragmentation in the past, you don't know why, literally this is the answer. You're basically taking existing files that have been fragmented or broken up into multiple chunks across your hard drive, and you're rewriting them in order to make sequential access a lot quicker and a lot easier. So this is something where it's going to really, so even modern hard drives and modern SSDs do defragmentation themselves. They do it on the background silently, but the physics is always the same. Having your data stored in order so it can be accessed sequentially is always better than having the random have to jump to different locations on your hard drive or your SSD.
Like recluster.
Exactly. You're basically rewriting all the data to cluster it all together. If it's all together and it's all can be read sequentially, it's just at that point physics. Like you're literally limited by how fast the platter can spin and how fast the arm can get to that sector with the data. And if you line it up, hey, sector falls to my lap, fantastic. Oh wait, it's not in place. Well, all right, our hard drive arm, you got to go search for it now. Good luck. Might take you a good millisecond or two. All right, any questions on anything we've gone over so far? Because I want to make sure we have the comfort over the physical storage before we go into a level deeper from that point. Any questions?
I got a question. That physical hard drive that you passed around, there's only one point where it accesses the data. So
Yep.
Is there any opportunity where it's multiple points, like a rake, where it can simultaneously look for data?
It's funny you say that. So from a hard drive standpoint, the head can only access a single sector at a time. So the answer is there's no way to access multiple sectors at once. You have to physically move the arm around. Now, what can be done, and this is a bit more in the weeds here, with hard drives and also SSD chunks called queue depth, where you basically request multiple things at once. And rather than the hard drive like accessing request 1 first, then request 2, then request 3, if the platter spinning, it says, hey, request 4 is on the way to request 2. Let me just pick up 4 on the way. So it's not really multiple raking, but it's more so it can kind of do things out of order in order to maximize the performance of accessing the data. And that also occurs in SSDs where the larger your queue depth is, the more we can kind of like cheat, do things out of order to best optimize what the hardware is allowed to do. All right, SSD. So what we talked about here about sequential access is basically the same for both hard drives or SSDs. They work physically differently. Hard drives are a lot more mechanical. That's why I brought in as a prop. You can physically see the disk, you can see the ARM, you can play around with it, you can see physically what's happening there. SSDs are all electronic, but even the fact they're all electronic, it's still way faster to have data be done sequentially than through random access. And to give some context of how SSD actually functions, the difference between a sequential read and a random read on an SSD is a sequential read basically can go from a beginning point to an end point on a chip and read all the way through. The controller of the SSD says, all right, your file starts in this location and keep on reading until offset finishes. If your data is fragmented in multiple locations in the SSD, the controller has to say, okay, I need to compute this sector first, then this sector second, this sector third at different addresses and scan through. It's not mechanical, it's a bit more nuanced. That's why I like the hard drive as a example a bit better, because you can actually physically see what's happening here. But the moral of the story is sequential access is king, and random access will slow down things dramatically. Any questions on anything we've gone over so far?
Question, a few slides back.
Go for it.
Column store versus row store. Is there a separate, are they? Data, is that exact?
A lot of people use different names for it. The key thing, and you're actually might be, hold on, let me just check real quick. Yeah, you're literally one slide away from the answer. All right, cool. Oh, I see another hand up.
How does the operating system play a role? Like,
Mhm.
there's a pagination, memory segmentation.
So that's actually a good question. So basically, the operating system will rely on your file system to access data. And the file system will record where each file, basically your file system is basically a lookup table where it says, okay, this file starts at this address. If it's all sequential, there's one address and you give the length of it and it reads the file across. If it's random, your file system will have multiple addresses saying, here's part 1, here's part 2, here's part 3. Your operating system will automatically see these records in the file system, and when you read a file that's fragmented, it treats it as one file from your standpoint. But under the hood, the OS is going, okay, well, I have to go over here first, and I have to go to a different part of the sector. Oh, wait, now I have to go to the third part of the sector. Rather than just one large, nice address, it can hop around. The operating system will handle that for you. All you'll do is wait an extra second to get your response back. Oh, what?
I'm sorry. Does your files only get fragmented if it's large, or is it kind of like you open up a file and then you edit some stuff so it changes the bytes in certain areas and that's what causes it to write again?
Both. So, and that's such a fantastic question. If you have a tiny file, it's going to write the whole file down, no problem. If your files, let's say gigabyte, and you have no individual, let's say, collection of sectors, so here the white space is open space. Start writing the file down, it's bigger than the space you have, like the file in the middle. You'll break it, have to go to a separate open space. So large files will tend to get fragmented more often. They don't fit in one nice write. Defragment, you literally shuffle things around so things can be all put together. That's item 1. Item 2, and you brought a really good point here. If your files are edited and there's something right after the file finishes, you got to write down that somewhere else and you got to defragment it. So if you basically at the end, if you write a fresh file and nothing else occurs in your file system, your next write will be right there, nice and order, be wide open territory. If you write to a file, leave it away for like a month. Come back. All right, you have all the other stuff now on the disk. Basically, you have if you're writing basically your file here, you stop. And so it writes something else right here, you got to continue somewhere else in the platter. And now you're just fragmented, you have random IO, and performance is hit quite heavily. That was an excellent question and 2 excellent points. All right, so cool. Any other questions on anything we've covered so far? All right, so now getting into the row store versus column store conversation. So this is something I put together very poorly, so I apologize. Basically, this is meant to be represent different tracks on a hard drive or an SSD and how data is laid out. This is an example of a row store. So we have basically row 1 continues, then row 2, row 3, row 4. The idea is this is how data can look in a row store table, and we're going to go over the characteristics of the data as you change the data or access it. So, question for the group: if I want to add a row of data, how does it look in this example? We'll just add one row at the very end. Real easy. Okay, let's say if I want to update a record, how do I do that? Ah.
Edit it and then save it.
Yep, and you can do it right in place. So row 5 gets overwritten, real easy. The rows is exact same size, not a problem at all. How do I delete a row of data?
Or is gone. Well, don't you like Tombstone or something and then the OS?
You're getting way too fancy. Think 1980s. Think 1980s, man. Yeah, bam, just erase it. You're done. All right, now here's the tricky thing. What if I want to, let's say, in this row of data, I have multiple different columns. I want to read one column, aggregate it up. What does the read look like? Pain, yes. You have a lot of random IO. In reality, a lot of, since the files can be very, rows can be very close together, it tends to be a sequential read. It just reads everything and throws it away. That's why in most relational databases, if you do like a count all, and it's like, or select count one on a table, by basically having to read the entire row, there's no performance difference between if you give a column or not, because it's reading everything and disregarding it too. So in row-based storage, when it comes to accessing and aggregating all the data, you literally have to either jump to the individual sectors or it's right next to each other. You read it and you just throw 8% of your data away because you didn't ask for the entire row of data. So this is some of the key pros and cons of row storage. Row storage makes adding records, updating records, and deleting records very easy because they're all the exact same size. It's the reading of records that ends up becoming painful. So if you have any transactional databases that like have a lot of credit card sales, right? It's live. This is fantastic for tons and tons of writes. It's problematic when you want to do large compute, let's say end of month reads. All right, cool. Any questions on row storage? Oh.
When you take place,
So the answer depends on your database. All right, so it depends. A database will actually have a collection of files, and the files have sectors that are collections of records. Your database should keep track of what spaces are open in those files, and when something's deleted, it will let you just delete the record. That's no big deal. But then you can fill another record in. I will note here, because of this, most data types are fixed. They don't really change. The exception are strings. Most databases for strings will not actually store your string in the row itself. It saves a pointer to an external collection. So that way, if you have a string that's bigger or shorter, you're not having to rewrite entire rows. You can just update records in place. Like here, you can update in place. So do note, if your file gets, so this row store is very focused on making sure your data, if you update it, you're not actually making the record bigger in place. You're just putting a pointer for dynamic length, and then things are fixed length, like numbers or dates. Those don't really change. Those are consistently sized. So excellent question there. All right, cool. Any other questions on row stores? All right, I'll take that as a no. So now getting into column store. Okay, so here is a column store example I put together again. The key difference is rather than storing each row, you're storing for a table each column one by one. So you can already see some of the benefits and the cons here by having everything with individual columns. If you want, let's say, aggregate, let's say a table that's 100 columns, and you want to summarize some data by individual thing, because if you have 100 columns and only care about 2 of the columns in there in that table, just read the data you care about. You don't need to read everything. You only need to read what is relevant to you, and you do not care about the other data because you only need to read what you need to. The nice thing here also is it's sequential. So when it comes to actually reading the data, just your head gets in place and you just read it nice and it's in order. So it really makes performance way better. Any questions on reading before we get to the dark side of this?
Then we have a rational.
A where clause. So if you have a where clause, you'll basically, so if you have a where clause, normal to do is read the where clause column entirely to apply the where condition. It finds out where it applies and applies in the second column. So let's say if you have real basic example, you have a table, you want to put one column from there and do a where clause on a different column. you basically have two hard drive scans of column store. You first do the where clause, figure out where it applies, and you get the second column. Or your database might actually read both in parallel and just say, okay, I'm going to read both. Your where clause is false. It's not going to return it, and then move on. Where it's true, keep on going along. Because with column stores, reading data aggregations are very, very efficient. This is why a lot of data warehouses are geared more towards analytical workloads. They are fantastic at reads, fantastic at joins, fantastic at a lot of analytical workloads. This is where data warehouses really, really shine. Any other questions on reads before we get to the dark stuff? You're getting to the very next, not getting to the very next slide. All right, so the next one I'm going to show is basically pain. Oh, hand up, yep.
How do you know if the data warehouse is column store or row store?
So I have two answers for that. The most common answer is most will usually default to one or another solution. Near the beginning, real quick. So I gave some examples of different databases and data warehouses. Most databases structure. Most data warehouses will default to a column store. So how the vendor advertise themselves, it's not guaranteed, but there tends to be a strong correlation where if you're selling your product more for transactional processing, you'll be more in the relational database side. If your vendor selling their database more as a analytical tool, it will be more towards column stores by default. I will say with that said, if you're a power user, you can actually on table creation define how it's physically stored, so you can change it. But most people don't define row store or column store. They tend to just default to whatever the database does, and that creates most data tools will default to presets that best are geared towards our marketed use case.
How large of the database would it be where it's a significant difference to performance?
Yeah, so the answer is it kind of depends on your use case. If you're trying to drive a UI, are not really driven much by the data warehouses. They tend to be driven mostly by relational databases because there tend to be smaller data sets that are a lot more live, active, and transactional. You might have every single sale for the day in a relational database, and there you might have thousands of records for that day, but thousands of records are not that much for an actual database. Where data warehouses really starts showing their advantage is when you have large data sets that are, let's say, weeks, months, or even years of data, how do you aggregate it all together? I'll put it like this. If your data is probably under 1 million rows of data, you're fine in a traditional relational database. When you start getting over we hit millions and millions of rows. I know before we've used where I work, we've had clients have a 1.7 billion record data set, and that's where putting in a data warehouse really, really helps us out to really optimize its performance here. All right, excellent question. Excellent question. Any other questions? Oh,
When you like update the column store, do you have to take like a lock on the whole database? Does it have to like stop additional writes?
so the answer is yes, but not just for data warehouses. Databases also do that too. Both are usually considered ACID compliant, which basically says, I forget the full acronym, but the key ones are consistency or completeness and atomic transactions. Whenever you have a database and you have reads occurring to it, the multiple reads occur in parallel. The moment you have a write, you want to make it where if two writes occur at the same time, they're not occurring at the exact same time in the table. One occurs, transactions recorded, and the second one occurs. If two come at the same time, one will be held back until the first transaction is committed, and then you move forward. This makes it so if you have multiple writes occurring to your table at the exact same time, they do not collide, they will wait sequentially in order. Now, with row store and column stores, they have different performance characteristics between reads and writes, but both will basically wait for the first transaction to finish before the next one can start. And that ensures that you have everything in order. And realistically, if something goes wrong, let's say you have to update two tables and it's all in a single commit. First write goes fine. Second write blows up, hits an error. You're going to roll it back and make it like it never happened. That way your transaction is complete. A perfect example is, let's say if you are a shipping company. So when you have a payment table and you have a sales table, what you don't want to do is have a record in the sales table with no payment. Then you're gonna start shipping goods for free. You also don't want to have a payment with no shipping document. Now you're basically stealing someone's money. You want that transaction to be complete, where if they're both not there, neither one's there. So that is a huge focus of asset compliance for databases. So excellent question. I wasn't planning to bring that up, but that is a fundamental value to why these tools exist. And I'll go a bit further. Programming databases is really, really hard because of asset compliance, but it's really critical because without it, your data is unreliable. So that's really, really fundamentally valuable. And that's an excellent point for bringing that up. All right, cool. Any other questions from anyone else?
Those storing databases, you can always get column store indexes for.
Mhm.
So can you explain then, is it really advantageous to go to a column store type of database dimension or do you use to make column store in the store?
So if I understand correctly, you're asking about indexing on databases and then changing characteristics. That's actually an excellent question too. So when it comes to indexes, the way indexes really work is they basically create a copy of a single column of a relational database, and they basically sort the data in that column in order, and they have pointers to the location on the original table. So you're basically, every time you create an index, you're creating a second little table of just that one column. So actually, is everyone familiar with what indexes are in databases or not really? Yes or no? It's a separate question. I'm sorry.
Oh, yeah, no, I was just saying.
Oh, yeah. Oh, sorry. So indexes are really a way to help optimize relational databases to have them perform much more quickly. And the way they really work, it's like almost like a cheat sheet to where to find the data in question that you care about. By ultimately taking a column, hopping to the side, storing the location for every record in that column, and then sorting it, you can start doing something called a binary search, where basically you have all your data in order, and you go, cool, I'm going to go, let's say you have records from 1 to 100, and you look for number 23. All right, I'll first go to 23 in the middle. Is it higher or lower? Oh, wait, it's lower than this. Half the table's already wiped out. I can go to the next part. By having your data pre-sorted in order, you can do scans way, way faster. And once you find what you're looking for, it has an address that points you straight to the correct table with the full values there. So that's how indexes work. They help massively with reads. The trade-off is every time you write to an table with an index, you have to update that index. And you got to pick your poison, make the writes go a little slower and make the reads go a little faster. So didn't mean to go into indexes, but it's a great point, and thank you for bringing that up. Any other questions on databases or any of the curveballs that you want to bring up?
Why does delete and truncate, why are they different as far as one locking the table, one not?
So in most databases, delete is a reversible transaction. So if it fails halfway through, it will reverse it. Most of the time, truncate doesn't have a where statement. It's just the entire table gets wiped. And because the table is still getting wiped, there's no like in between state. It basically forgoes the ASCII compliance to have the whole delete go faster. And usually if you're deleting a whole table, you're not. All right. So a database still exists on the computer and it still says it's files in the file system. Deleting an entire or doing a delete command will scan through the individual records in the table and find which ones need to be removed. Truncate goes, I'm just looking at the file. I'm not even gonna look at the file. I'm just gonna delete the whole file right there. So that's an excellent question right there. And that is a different forms characteristic, but yes, it's a good one. All right, any other questions or anything right else we've gone over so far before we get into the pain points of column store? All right, so getting to the pain points of column store is anytime you want to modify the data in the column store, the big trade-off is you basically have to rewrite that entire column or sector of column in order to get the data to be complete. In the prior example here, the first column is provided here. If let's say if I want to add a single record to that column, I can't because there's another column right there, starting right after that. I can't just extend the column here because there are data elsewhere in the drive in its place. To add additional data, I basically have to take the entire column, rewrite the whole thing, and then add like a little bit of extra data to it. If we're going to update records too, if the data is the exact same size, you can tend to keep updates in place. But if it's a different size, you have to rewrite the data again. And if you're deleting data, Most database tools will actually rewrite the whole column again anyway to make sure you don't waste space and you have no residual value. This is the big pain point with column stores. For month-end analytical workloads where you write data once, it's fine paying the tax. But if you have someone, let's say you tried using a data warehouse for a sales system, a live system where you have sales coming in every minute, do you really want to rewrite your entire table every minute because someone added one row of data? That would just massively hurt performance, and that'd massively hurt the performance characteristics of your storage medium. So any questions on updating the, oh,
Yeah,
go.
for the update phase, like, what if you hypothetically had like, let's say you like had a restricted number of columns, so you put each one on its own file.
Mhm.
Every single time a row comes in, you guarantee that you never want to like change the value, you only want to append. Why not just add to each individual file?
So that's where it gets interesting. 'Cause I know you said you work at Databricks. Since most data warehouses will want to keep their sectors in order. Databricks is unique because using Parquet files or Delta files, it can actually append files on there. The trade-off with that though is if you have, let's say, 1,000,000 individual inserts, you'll have 1,000,000 individual files in your for your Delta Lake file, and the I/O time to actually access each file can create a bit of overhead. So there's still a trade-off there. That's also why with Databricks, the vacuum command is really nice. You can remove all the layers and you can rewrite all the individual rows in order to get that sequential functionality again. So, oh, I see some more hands up. Yeah.
Isn't there like there's like a data structure that does that, right? It's like a SST, like some type of binary table or something.
There may be, I don't know what that is. I don't know what that is. Unfortunately, I apologize.
I'm assuming that there are databases, like if you have a columnar store, right, you could have some sort of buffer where it's like leave space for, like you analyze how much is being put into it, right? It's like, okay, we're gonna leave this much open, then next time it'll like extend it, right? Is there like, I'm guessing, is there performance tradebacks for that? Space?
Yes. So well, you can leave empty space in there. Most databases that support column stores use sectors, so you don't really have one column altogether. You tend to chunk sectors or chunk multiple values of a column together. So you might have, let's say, 100,000 rows of data in a single sector for that column, or you have 1,000,000. And the trade-off is the bigger the sector, the faster the reads are, and the slower the writes are.
So that's like micro partition, right? It's like,
Yeah. Exactly, and it's a trade-off. The more small partitions you have, the slower it hurts. But also the more larger partitions you have, the more it can be done as a single operation. And I'll actually pivot to a question from the very beginning about data and parallelism. One nice thing with column stores too, with individual sectors that they have, if you have a single table, a single column that's in 10 sectors, you can have 10 different threads of IO reading 10 sectors in parallel and running in parallel also. So by having basically, let's say it's having one more column here, you get the column broken into chunks. You can have it where each thread or process reads each individual sector and continues on until it reaches the end of that sector. So it's these tools, I'm kind of exaggerating, it's one massive column. These tools tend to chunk it into bits, but you're talking about chunks of 100,000 records at once, and that can change the performance characteristics. So I want to get back to that question from the beginning and make sure we covered accessing data in parallel. All right, cool. Question.
Can you explain a little bit more about the trouble with updating the row? Because I understand with adding and deleting, you're changing
The shape.
Right, but how does updating?
All right, this is something I didn't mean to get into, but I'll get into a bit. So most column store data, you don't actually store the raw values together. Most column stores, what they'll do is, let me see if I can actually go on a little tangent here. If I can, presentation mode. So sorry, this is something I didn't intend to do, but this will. Cool. So most of the time when you access a single column of data, let's say here, you're not really storing that column in there directly. What you're really storing is what's really happening under the hood is that column is really being stored as two different objects. So let's say if I create one object here, I'll create another example here. So let's say if I call this A, can I make that a little bigger? I make that darker too, so it's more visible. Okay, cool. So I have A, B, C, D. Okay, so what's really happening, and a lot of times when you do column store, is, let me add, it's not actually storing the string value in place. It's storing a pointer. So this will be 1, B will be 2, A will be 1 again, 2, C will be 3, and D will be 4. And then in a lookup table between the two, you'll have a comparison where 1 maps to A, 2 maps to B, 3 maps to C, and 4 maps to D. So you're right that if you're, so with a, all right, so the actual value of strings can be fairly dynamic. And this is something where having strings that are, let's say, 10 word long, like names, they're not all the same size. To have column stores be more performant, it's not uncommon for days to repeat a column store over and over. Let's say you have a column of states in the United States. You only have 50 values. You don't need to store the same string over and over and over again, because strings are much, much larger storage than like a number. So a lot of times in column store, you'll actually store an index or a unique pointer to that value, and you'll do a lookup to it. So here, this A might be like, for example, let's say this is like 3 kilobytes of data, for example. The pointer is a few bits of data. A lot of times to store and people the values repeat over and over, you store the individual IDs that map it, and you build a lookup table for comparison. So that helps really reduce and compress the size of column store and helps read performance. Now getting to the updates, the issue here is in info sector, these two items are basically, both the lookup and the values are both scrunched together. If I were to update C into B, C, something longer there to make it a bit more larger. The problem if I do that, now your column, the sector it's stored is a different size. So even updates will change the size of the data, and it's not an update in place, and that makes it more difficult. So column stores, even for updates, have to do a full rewrite. Does that help answer the question? All right, so I didn't mean to get into that, but you asked, I'm like, all right, going down the rabbit hole. So excellent question, though. Let me get back to the core presentation. All right, oh, don't want to get, so any other questions on column stores and writing of data before we continue further? Oh,
That's hard to update anything with a column store. Why use it?
because the reads are real fast. That's the trade-off. And that's the thing here with the physical storage. And this is where I'm going to be maybe a bit of a cynical person. It's not uncommon for vendors to go, oh, we can do these reads fast, we can do this fast. When it comes to the physics of your actual storage, there are trade-offs between reads and writes. Column stores that maximize read performance at the cost of write performance, while relational databases benefit or focus on writes at the cost of making reads slower. So it really cares what you care about, because physically you have to store it on a hard drive or SSD. To say you still need to store it somehow, and the storage has its limitations. I don't care if you're using hard drives, SSD, NVMe SSDs. There are trade-offs, and there's no free lunch. And it's not common. People go, oh, if you do this, it's faster. It's faster in what use cases, what trade-offs? Never for the lunch, especially when it comes to mature software.
So would that be better, like, she's talking about the write performance, right? So would it be better like batch them and then you write all of them?
Yes. So when it comes to column store, a small write and a large write are basically the same amount of effort either way. So if you're updating, let's say, a single row of data in a column store, it's really, really expensive. Now, let's say if you have a table that you update once a month at month end close, cool. I'll wait the extra 30 seconds. I don't care. It's done once a month. Not a problem at all. But I can't wait 30 seconds per user in my UI with thousands of events occurring per hour.
So would you you have like your Postgres or like your row table or your database? Would you like duplicate it at the end of the month or something into the column store and run the query?
Yes, that's actually super common, where people will, for like data warehousing purposes, they'll keep about a year of data in their normal database, and then they'll dump the past 5 years of data in the analytical database. And the data scientists and data engineers go crazy on the analytical database to try figuring out insights and answers from it. Because you're like, cool, let's say if I'm Walmart, I want to analyze these strawberry pop charts for whatever reason. I have one database recording the sale of everything, and they have another database that has all my sales for the past 3 years. And I'll scan it for strawberry pop tarts. Okay, I'm willing to pay the cost of the read on analytical database because it's way, way faster. And I don't want to slow down my production database that's being used right now from Walmart. I can't have, no, I can't stop selling stuff for someone to run an analytical query. But if I copy all data over, I can basically have someone read in parallel and really have the data written in a way that's best aggregated for that use case. So it's not uncommon where people will have two copies of data, a live system and then an analytical system, and updates either nightly or end of month or whenever. Oh,
So there's half dozen or so data warehouse drops companies out there. What differentiates them? How much of the differentiation is related to you have really good people implementing for you or not? 80% of it is just work, 20% is really the products don't differ that much. And
so my answer is it depends. If it's like a newer database technology, it comes a lot down to skill. When it comes to really mature tools, things that have been around for over a decade and are used by millions and millions of different consumers, that's where things have reached like maturity kind of plateaued a bit, and you care a lot about the feature set and what's being available to you. But the physical storage medium, that physical storage medium is something where the characteristics of it, like there's no silver bullet here. So when it comes to mature tools, the performance is fairly similar. When it comes to newer tools, they can be a lot of new features. That is where things get really nuanced, interesting, and a lot more can vary from vendor to vendor. Did I answer the question you're looking for, or answer it depends. Yeah.
Storage is the same, the feature set, like things like that, we have to, we're putting in tools so that we can get the job a lot quicker done. But I want to ask you a question. It's a layer there, when you are talking about storing data and whatnot, that's all physical, but then there's a layer of logic that the database uses, pages and extends that.
Yep.
Rules. What's the overhead there?
So the answer depends on the operation you're doing. From my experience, for very large data sets, accessing data on storage from REST ends up being around 80% of your overall runtime. The compute can vary dramatically, but if you do things in an efficient manner, you can optimize that second layer. You can optimize that. You can tune your queries for it. You can put indexes in place. What you can't do is you can't make the storage layer go any faster. That's something where you're stuck with it, and you have to live with that. So there's no way to optimize that other than what the storage can physically access. So to answer your question, or all right, cool.
Say, for example, let's see where
Mhm.
you'd say, like, what's the difference? Like, how would you choose if you were a business and those
Mhm.
they're both relational databases, and why would you choose one or the other?
So realistically, it comes down to the feature set you care about. I will say most of these are open source tools. So Postgres, MySQL, and SQLite are open source. The feature set is SQLite is the easiest to work with, but it's also just a local file on your machine. And it's good for like embedded devices. It's not really good for SQLite doesn't allow multiple people to read and write at the same time. That's the trade-off there. MySQL and Postgres can allow you to read data is meant more for a shared data solution, allowing for multiple concurrent operations to work. SQL Server is a Microsoft product, so if you're really close with Microsoft, that makes it really convenient. And Oracle is if you want to deal with lawsuits all the time. Yeah, money. Yes, that's a big part too.
Like the upward and another three.
Yep. Also, MySQL is free too, but Oracle bought MySQL, and there's a fork called MariaDB. It's a whole set of drama. All right. All right. I only got about 2 or 3 more slides left, and then I can go into full question mode. So we talked about the trade-offs on the right side being very taxing. So key takeaways, we kind of went to already. Row stores are really, really beneficial for transactional processing. They're not that good for large aggregations, especially with a lot of random I/O involved. Column store is great for analytical workloads, great for reads, great for performance. But if you have lots of small individual writes, column store gets very expensive. Large writes, not that bad. Tons of little writes, though, that tends to really hurt column store significantly. And the silver line to all of this is most mature database tools will let you pick and choose. They'll default to something for you, but whether you're using Postgres or MySQL or Databricks, like a lot of different tools out there let you pick different storage mediums that can change the characteristics and really make it what you want to do. So getting to the point mentioned earlier, pick a database you really like for its feature set, take a database you're comfortable with, and see if it has multiple options available for storage, and that can really give you the benefits of row store versus column store and different trade-offs between the two. All right, and that is my presentation there. Now I'm going to open up to all questions before we run out of time in the next few minutes.
So just heard that it's you're limited by the physical layer how it's stored, right? Is there one of the things you mentioned is like part of the optimization from the operating system, right?
Yes.
And as far as I know, like most operating systems, right, is it like Linux, the whatever the Apple OS, right?
Yes,
and then Windows, right? And is there anyone or any of those? I don't know if those three aren't, but are there any of those like optimized for like databases? Like I feel like a database is just like something that not just sits on top of the operating system. It's like a computer, but it's not.
All right, so I'm going to nerd out real quick. A lot of the operating system performance file system they use. If you're using something like Windows, the NTFS file system, most modern file systems are journaling file systems. So they'll do a event on the file system, record as complete, and then you kind of get like a second layer of ACID compliance. Extends for NTFS and AFS. So basically the Windows file system, the Linux file, the default Linux file system, and the Apple file system all basically are journaling file systems. Once you start getting to really unique things in the Linux world, you can get things like ZFS or BTRFS, which are copy on write file systems. Those will actually hurt your database performance, but they allow for things like snapshotting and ability to reverse the clock. So there's almost always trade-offs involved with the file system you use. The file systems with snapshots, ability to revert to an earlier point in time. The file systems actually let you create copies of it and fork it live, and you had two mirrors of the same system with duplicating data. Those are really nice features, but they hurt performance. So you really need to pick and choose. If you really want to maximize performance of your file system for your database, you're probably better off in Linux picking either the extends4 file system or the XFS file system. Both of those tend to be fairly light, and they focus heavily on journaling, but they don't focus on any kind of like copy on write functionality. So they tend to have less overhead, higher performance, but you also get less bells and whistles. You get no snapshots. You have to, if you want to have your copy of your data at a certain point in time, you'd like to physically copy it. So it's trade-offs when it comes to file system choice.
Okay, I'm not a database guy. I'm not sure I got everything done, but I think I fundamentally understand that if you put a query in either one of these, you're going to get exactly the same answer.
Yep.
And faster or slower. Okay.
Correct.
Now, this is a little off text of your talk, but like there's big data out there, right? Big data, and that isn't going to give you the same answer necessarily as these, right?
Well, it depends. If you're using a, so let's say, I'll have to use Databricks example because we were talking earlier. So let's say if you use Databricks for your big database and big data analytical purposes. Databricks will store your data by default in column store, and it allows you to store your relational data in a column store format that makes it more performant. Really the big users of column stores initially were all the big data tools. They were the ones that really were able to benefit from it, and they're the ones really help maximize it. If your big data is relational, as in it's a tabular structure that can be accessed via SQL, you're better off using a tool that can support column store, because that tends to be one of the best ways of storing your data. And even with the big data solution, they may be fragmented across multiple clusters and multiple locations. So you have multiple machines. You still tend to want your data stored in a column store, because in big data, you tend to have a lot of reads. You don't tend to have a lot of writes being done live. You tend to have a write done at the end of the month or the end of the quarter. And I see you got,
Okay,
question?
So I think I'm missing something. So you mentioned ACID. I vaguely understand what that is. Okay? In transactional database, we didn't kind of get with that. My sense is that big data doesn't have that characteristic necessarily. And the thing when I, as an engineer, was reading specs on a big data, I got to this optimistic concurrency control. Like, if you're lucky, you get the answer from here or from here. If you're lucky, you'll get the same answer. Maybe not.
So it's actually funny you do say that, because So usually data warehouses here. I do know single source ASIC compliance, Teradata ASIC compliance, Databricks also allows for ASIC compliance, stuff like Hive though. If you're using a lot of the Hadoop ecosystem, they actually forego a lot of the data integrity checks for higher performance and higher scalability. Most data tools now have tried to still bring back in ASIC compliance for data integrity purposes. But if you go, let's say, like Hadoop, or maybe more of the first gen of big data tools, they actually,
It's one of the.
Yep.
popular, no,
and they took away a lot of the safety controls in the name of performance, and they got it.
not ASIC.
Hadoop is not ASIC. So technically speaking, Hadoop is a file system. Hive basically lets you read
All right.
primarily CSV files or Parquet files on Hadoop.
Okay, so for the naive guy like me, I can just say, is your database ASIC compliant? And if it is, then I'm happy with transaction, blah, blah, blah.
Yes.
If not, then they're gonna wave their hands and smoke and mirrors and.
Yeah, and then
I know it's optimistic.
yep, and then you'll get a call at 3 a.m. in the morning going, yeah, production is down, something went wrong, or hey, the financials don't tie out. You're like,
Thank you.
so
Is he talking about like the consistent snapshot isolation level of like databases?
not necessarily. What he was referring to was a lot of the original big data tools that took away a lot of safety controls. So you're basically like, oh, like meant to drive a car. Analog brakes, it's too much weight, take them off. Traction control, don't need that, take a airbags, don't need those either. So a lot of the original big data tools a lot of the safety controls went away, and the idea was, the initial mentality was, your solution will scale, but it will forego accuracy as a trade-off.
Okay.
So it's become less popular as time has gone on, but there are certain tools that got really, really large that still leverage those kind of lack of safety controls to go. The question is, what do you care more about, accuracy or scalability? If you don't care about accuracy at all, then you can go full scalability, but there are trade-offs and you can have a bad time. All right, I saw some more hands up around here. Additional questions? Oh, Mhm.
They're managing for you, like what tools can you play with and what levers can you pull?
so the answer to that, it depends what the vendor gives you. So for example, actually I'll use Databricks again because I use that for work and I know you know that too. For most vendors, when you get Databricks to serve, you have a lot less knobs and dials you can tune into, but they'll still expose some things. I know Databricks allows you to pick the storage medium available. If you don't give it a storage medium, it will default to Delta table, which is basically Parquet. But if you want to change something to, let's say, an OCR format, ORC file format, or if you want to use an Avro file format, those have different trade-offs. Some are column store, some are row store, but most database like solutions offered by vendor that are more turnkey, they don't give you those knobs and dials to turn because they're trying to give you more of a turnkey, easy solution. I know Databricks gives you some more knobs and dials to turn via your create table statements, but in other database technologies, I'm thinking they don't always give you that option, and you're kind of given what you're given, and you kind of live with it. So yeah.
Yeah, on that note, I think Snowflake, you can ingest all those types of data, right? You can just Starlink, I think you can Parquet, but it's like, I think it just stores it however it's normally stored.
I could be wrong, because Snowflake's proprietary. I don't have visibility to their source code, but my understanding is that you probably use a column store for Snowflake, and they really gear it for analytical use cases. Like if you see a vendor saying, we're analytical, it's probably column store.
But the actual like file format is which is open source.
Oh, okay.
Header to do Delta. The other third meaning is Apache 2D, but no one really.
You know, I thought Hive was underneath Databricks. Is that not the case? Is it?
Hive is.
So well, not yeah.
Databricks uses Spark.
Mhm.
Spark. So Databricks is a Spark shop. So Databricks has Spark and it has Delta Lake. So that like, so Spark is a compute engine for distributed computing and Delta Lake for you have to like storage of Parquet files, just like metadata of Parquet files. Right. And Snowflake has their own proprietary data engine. And they also have on the side, they have open source. So Iceberg is completely open source. So Delta Lake is Databricks. Delta Lake, they both it's complicated. Delta Lake is open source, but Databricks has their own internal version of it, but it's just very similar. Apache Iceberg is fully open source and backed by a lot of companies like Netflix and Apple. But that's sort of like how that ecosystem works. Hive is separate on the Hadoop distributed file system, which like is even more complicated. So like on the side.
And also, I'm sorry, go ahead.
Spark used to sit on top of Hive, right?
It can. So Spark can use Hive as a metastore. Yeah, let's not afterwards. We're getting even more in the weeds there. But what I'll say to you is all we said right here, all the storage tools have to pick between row store and column store.
Right.
This concept will hold true no matter what tool you use. Why I bring it up. So when someone said, blah, 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 okay, row store, column store, blah, blah, blah. Okay, row store, column store, but this is physics. I don't care what you're telling me. I need to know which one it is.
All right, sounds like we're gonna have some good breakout discussions after this. But I don't want to break the broken
Oh, there
hard
is.
drives.
They were broken originally, so yeah.
Yeah, thanks very much, Alex. That was awesome.
That was something that fell out, one of them.
Membership never ceases to amaze us, right? Every month we